Kader, are you there? I think he's joining. Jamal?
Hello, doctor.
Okay, you already joined the group, yeah?
Yes.
Okay, it shows me pending now. Kader, I think Kader. No. So, welcome to our third lecture on modern antenna system engineering. Last time we have discussed about antenna parameters, and I just would like to revise some of them, like antenna efficiency that we have discussed last time, and then actually formulating antenna efficiency. We have assumed the transmission line to be lossless, whereas when we come to the practical world, we can't come up with a lossless transmission line. So just to make or to have a kind of general formula for antenna efficiency, I have tried to include the antenna loss, so that we would like to have an expression for antenna efficiency which account for the reflection loss due to antenna mismatch. Antenna mismatch. Actually, in our previous formulation, we have taken into account the conduction and dielectric loss. Now we would like to include, I think people are, joining, leaving and joining the social. Let me put it here maybe. So for the conduction loss, the efficiency associated with conduction loss is represented by EC, and the efficiency which is associated with dielectric loss, it is represented by ED. Normally, these are the loss which account to the antenna loss, internal loss of the antenna. Whereas ER, which is reflection loss, which happen due to transmission line and antenna mismatch. So we have incorporated this efficiency so as to have a general. Is that clear? The audio? I'm hearing some echo, yeah? Or is there anyone who didn't meet? Yes. Yeah? Kapisa, yours is not muted, I think. Masfin too.
Yes.
Please mute. Daniel, please. Kapisa, I think you also better mute your audio. Masfin, yes, thank you. No, that's okay, thank you. Now, okay. I think now it is clear, yeah? Good. So the general or overall efficiency of a radiating element or antenna can be given by this expression E0. This is to account for all type of losses in antenna system, in antenna system. So this is an expression for antenna efficiency. A0 accounts for the total efficiency, which is actually the efficiency of all, whether it is reflection efficiency, conduction efficiency, or dielectric efficiency. They are efficiency. So efficiency by its nature is dimensionless. So it is there. All of them are dimensionless. We have here the voltage reflection coefficient, which is calculated at the input terminal of the antenna and can be expressed in terms of, you see, the input impedance and the characteristic impedance, you see, of the transmission line. We can rewrite the voltage reflection coefficient in terms of this impedance. And basically, it is difficult to calculate, the conduction and electric efficiency of a given radiating element independently. So the common technique is to make a measurement. From the measurement, it is possible to have an efficiency for the conduction and electric, just like a lumped form, you know. So what we're gonna do is, after measurement, we can bring back into an expression that we have developed, so that we can have an expression for the antenna efficiency in terms of the measurement, the efficiency measurement data. Then we can again formulate the general efficiency of the radiating element by taking account the transmission or reflection efficiency of the transmission line due to the transmission line. So this is what it looks like. Now we have the reflection efficiency. We have here the conduction and dielectric loss efficiency. Then we can rewrite the reflection efficiency in terms of reflection coefficient, and in terms of the voltage coefficient here, the voltage reflection coefficient. We can rewrite, you see, and we can have an expression for antenna efficiency in terms of the conduction dielectric coefficient, and that of the reflection coefficient, voltage reflection coefficient. This expression, that means the ECD, which is what you call it, the antenna radiation efficiency, because it is totally associated with the radiating element. So the antenna radiation efficiency can be expressed by this expression. That means ECD. ECD is the antenna radiation efficiency, which account for the loss due to the conduction and dielectric loss of the radiating element. Normally, this expression can be related with the gain and directivity of the radiating element. That means the antenna radiation efficiency can be expressed in terms of the gain and directivity of the radiating element. So you can associate this formula with gain and directivity. So the antenna efficiency take into account the reflection, conduction, and dielectric loss. That is the point that I just would like to emphasize. You see, the antenna efficiency takes into account the reflection, conduction, and dielectric loss, which means the efficiency of due to reflection efficiency, the efficiency due to the conduction loss, conduction efficiency, the efficiency due to dielectric loss, dielectric efficiency. So we know that we use RL. This is just generally to represent the conduction dielectric loss. That means the loss which come due to the conduction in dielectric element. So we represent this loss by capital RL. So the conduction dielectric efficiency is defined as the ratio of the power delivered to the radiation resistance, R, to the power delivered to the sum of the reflection loss plus the radiation efficiency. This is the formula. We have seen this for this model. The only thing I did was just I have tried to express the antenna efficiency. Antenna efficiency when the radiating element is assumed to be lossless. That means there exists no reflection. That means all the coming voltage is transmitted to the radiating element or delivered to the radiating element. For such scenario, for such scenario, we can assume a transmission line. For that reason, the reflection coefficient become, you see? Okay, they are disturbing, they are joining and leaving the room, you see? So we can rewrite the conduction dielectric efficiency of given radiating element in terms of the resistance. That is the additional formula. This is actually the previous formula we have derived in our previous class. The only thing we have tried to rewrite it in terms of the resistance of the different node. Then we go directivity. We have already discussed this. Now I just go back to antenna polarization. Was Noi? I think someone had a question, yeah? Was that Noi or who was that? In our previous class, someone was raising a question, yeah? While the conference was interrupted.
Yes.
Who was that?
Yes, it is me, sure.
Yeah, Noi. Could you mind to remind us because I think your question was something associated with polarization, yeah? Or something different?
Yeah.
Okay.
Yes.
Would you
the helix polarization happened in antenna?
Helix, which means elliptical, yeah? Elliptical polarization. It become helical. Normally, spherical polarization has a nature of, helix structure. Whereas when the magnitude, because when we are discussing about polarization, we are talking about the direction of the electric field, yeah, the orientation of the electric field. If the electric field is oriented, yeah, as the electromagnetic wave propagate, if it traces like a linear line through a medium, when it passes through a medium, when it traces a linear line, we call it linear polarization. Whereas when it traces like a circle, you see, we call it circular polarization. But it's a helical, like, the movement, the electromagnetic wave propagate, you see, in a direction which is perpendicular to the electric and the magnetic field, yeah? So in that case, it shows like an elliptical nature, helical nature, you see, which is to say that upgrade. What is it is to say that the electric window away from hello. Hello? Hello? Hello?
That's for me, doctor.
Yeah. Okay. Now I think now you hear me, yeah?
Yes, sir. We hear you.
Yeah, okay.
Yeah.
So the pattern, you know, it trace is what you call it polarization on a medium. So the helical structure is the movement, you see, it changes its direction in a circular fashion while making the direction of rotation or movement of the electric field. If the electric field is are oriented in a perpendicular direction, that means, for example, if we assume a spherical coordinate system and one polarization is along the phi and the other polarization is along the theta direction, you see, if the magnitude of these electric fields, you see, which are perpendicular to each other, if they show different magnitude, normally it shows an elliptical phenomena. You see, it traces an elliptical shape. But for both circular and elliptical scenario, it traces like a helical structure. Yeah. Hello, Noai.
Yes, yes, doctor.
Yeah, it traces like a helical structure. You know,
I'm hearing.
the electric field shows helical structure. That means the change, the time instant of the electric pattern. You see, if you follow, you know, the trace of this electric field variations versus time, you see, it's you observe like helical, you know, phenomena. Did I get your point?
Yes, doctor.
Hello.
Yes, yes.
No, your question was what is a helical structure? Why it is making a helical structure? Or is that something like that? That's what I
Yeah.
understood.
How it makes helical.
Okay, that means it is
How
actually
it makes helical
shape.
yeah, the shape. Yeah.
The shape of the electromagnetic wave.
The propagation of the electromagnetic wave.
Yeah,
Yeah.
that's good. So the
How
shape,
it will
yeah, you
make
see the shape. You
helix.
see,
That's my question.
yeah,
And thank you. I got the answer.
you got the point. That, you know, basically it's shaped by default, whether it is circular or elliptical. It shows helical structure. Yeah, but the point is, we have an electric field. If it is going to be a rectangular coordinate system, for example, we could have an electric field which is in the direction of x and the direction of y. You see, while it is rotating, you see, it make helical structure. That is the default. You see, as you measure the propagation of the electromagnetic field versus time, the propagation of the electromagnetic field make a helical pattern. Yeah. But this helical pattern, when it passes through a given medium, you see, it traces some pattern. That pattern is what you call it polarization. For circular, the pattern, because of the electric and magnetic field that are oriented in perpendicular to each other, since they have equal magnitude, the trace they left will be equal, which means circular pattern will be observed for the case of circular polarization. Whereas for the case of elliptical polarization, it shows an elliptic shape because the electric and the magnetic field, the electric field in the perpendicular direction, these two electric fields, they don't observe equal magnitude. Equal magnitude. This unequal magnitude results in a pattern, what you call it, an elliptic trace. An elliptic trace. Actually, this is very interesting. You know, I just would like to take much time discussing about polarization because this is somehow a confusing, yeah, phenomena. Why? What is the need to polarize our system? Why would we polarize our radiating element? Why? Brooke. Mr. Brooke?
Sir, yes.
Would you have your say? Would you like to comment on this?
I don't understand the question.
What is the need to polarize a radiating system? What is the need for polarization? Why we polarize? For example, while the broadcast stations, like if you look at EBS or ETV, EBC, or any, broadcasting station, they promote their, polarization, yeah? What is...
Okay, I think to increase the efficiency during receiving, we need to increase the efficiency. I expect that polarization is required for increasing the efficiency.
To increase the efficiency, that's right. What do we mean by efficiency here? Jamal. Hello, Jamal. Hello, Jamal. Okay.
Hello, doctor.
Yeah.
Hello, hello.
Did you hear the question? Did you?
The question, repeat me for me, sir.
Yes. The question is, what is the need for polarization? And what do we mean by, Brooke said that polarization is maximize or improve the efficiency of reception of the signal reception. So in terms of reception, we have said that. In terms of efficiency, we have said that it is input to an output. What do we mean by efficiency for the case of polarization?
Because we can use this polarization to configure the antenna's efficiency in many directions. For example, because in different cross polarization or another types of polarization, the antenna can be improved by using this polarization depending on environment we can use.
Good. Now, so far we have been discussing about polarization, about the pattern it makes, while it passes through a certain medium. Yeah? That was what we were discussing. Now, how we can physicalize this concept, how we can physicalize it?
By using a radiated different electrical field. We may physical, or we may become as
okay. አሁን ሶሪ ታይም አውት ሊለን ነው። አሁንም ይሄ ኮንፈረንስ እንትን ከእንደገና ሪስታርት አደርገዋለሁ። እሺ ካቋረጠ እንትን እንዳትሉ ነው ለሁላችሁ ኢንፎርሜሽን። ሶ Daniel, you hear me?
Yes. Yes, doctor.
Yeah. What do you think? As far as polarization is concerned, we were discussing